Good morning. So the video that I posted last Friday was for combinations, and that's pretty straightforward, and most of you probably had a fairly easy time with that. So I want to sort of illustrate, again, the difference between permutations, combinations, and then what we're going to do today. So let's just say, hypothetical situation, I have a bookstore, okay, and I've got many different titles. And of every title, I have many books. So let's just keep it really simple. If I had 20 titles, and let's say I have at least 100 of each. This is a bookstore, right? So I got a lot of books. Now, I want to buy some books for my friends. Maybe it's Christmas and I have 5 really close friends and I want to buy a different book for each one. I don't want to be, oh, I'm going to buy one book and give it to all my friends. No, I'm going to buy 5 books and I'm going to give one to each of my friends. Now, first of all, how many ways can I do that? I want to buy 5 books, one for each friend, and each book I want to be different. So if I pick books A, B, C, D, and E, then friend number 1 can get book A, B, C, D, or E. So there's multiple choices for that person. So in the first case, the question I'm asking is how many ways can I give 5 books to 5 different books to 5 different people? That would be permutation. But of permutation of what? I have 5, I want to give 5 books to friends. How many am I choosing from? I mean, technically there's 2,000 books at this bookstore. Am I choosing 5 from 2,000? Am I choosing 5 from 100? Am I choosing 5 from
20?
Choosing 5 from 20. There's 20 different titles. I want to pick 5 of them and give them out. So the first question, how many ways can I give 5 books to my 5 friends? Okay. Now, let's say the following week I go back and I said, wow, that was so successful. And I just gave 5 fantastic books to my friends, but I should give some to myself, right? I mean, reward yourself first. So now what I want to do is I want to go in and I want to buy 5 books for me. Now, obviously, I'm not going to buy the same book 5 times. That wouldn't make any sense. I'm going to buy 5 books for me. How many ways can I buy 5, again, different books? How many ways can I buy 5 different books for myself? Is that also a permutation? If I buy books A, B, C, D, and E, is that different than A, C, D, E, and B? Or are those the same 5 books?
They're the same.
So in this case, does the order matter at all?
It does not.
It does not. So when I'm buying them for me in the second case, this is the answer, which is much different. Let me grab my calculator here. In the first case, I'm ordering the books, okay? Because the order I grab the books is the order I'm giving them out to my friends. So in the first case, there's this many different ways. But in the second case, when I'm just grabbing all 5 for me, okay, it's a much smaller amount. This is only 15,504. Oh, now let's suppose that I said, you know what? Let's say I have 5 classes, and on the first day of class, I just want to give a gift of a book to anybody, but I don't really care who I give it to or what book I give it to. I'm just going to give out a book, 5 times. Technically, I could give out the same book 5 times. I mean, who's going to notice the difference? Because I'm not giving it to the same people. So class 1, I'm going to hand a book to one person. Class 2, I'm going to hand a book to one person. So technically, I could choose the same book 5 times. I could choose 5 different books. And, the ordering and all that, I don't know. That's neither one of these. So that's the situation we want to look at. What if I can reuse one of my choices? Now that's a fairly complicated derivation, but it's a very simple formula once we derive it. So let's consider, I'm going to start small and we'll work our way up. All right. So let's consider, I have the set of numbers. I have the set of numbers 1, 2, 3, 4, 5. And if I said to you, can you let's just say we want to put 2 numbers together. Well, if it's a permutation, for the permutation, we know that I could do this. I could go 1, 2, 1, 3, 1, 4, 1, 5, 2, 1, 2, 2. I'm sorry, not 2, 2, sorry. 2, 3, 2, 4, 2, 5, 3, 1, 3, 2, 3, 4, 3, 5, 4, 1, 4, 2, 4, 3, 4, 5, 5, 1, 5, 2, 5, 3, 5, 4. There's exactly 20 possible outcomes if I want to do a permutation choosing two of those numbers. Here's what they are, exactly 20. That would be permutation 5 choose 2, which is just 5 times 4. Now, what if I want to do a combination? Well, if I do a combination, then I'm just saying I'm picking two of the numbers. It doesn't matter what order I put them in. If I'm doing a combination, then some of these have been double counted. In other words, 1, 2 is the same as 2, 1. Oh, and 1, 3 is the same as 3, 1. 1, 4 is the same as 4, 1. 1, 5 is the same as 5, 1. 2, 3 is the same as 3, 2. 2, 4 is the same as 4, 2. 2, 5 is the same as 5, 2. 3, 4 is the same as 4, 3. 3, 5 is the same as 5, 3. And 4, 5 is the same as 5, 4. So if I said, let's do a combination of these numbers, we realize now we're down to 10. Okay. So in the first case, it was permutation 5 choose 2. The second case, it was combination 5 choose 2. So that's one of the really simple illustrations as to how I can get different answers. But now what if I said, I just want to pick two numbers? I don't care if they're the same or not. It'd be kind of like saying, I'm going to go to an ice cream store. The ice cream store has 5 flavors. I want a bowl with 2 scoops in it. Okay. Can I get flavor 1 twice? Is that illegal? Or is that totally okay? Oh, so if I go to the ice cream store and I say, I want to get 2 scoops. Okay. So how many ways could I do this if I'm allowed to repeat? Now, okay, if I go back to the original, is it the same, guys? Yes, it's the same ones, but there's a few more perhaps. Now, I'm not putting them in order. I'm just saying, I'm going to just take 2. See, when I get the 2 scoops of ice cream, you don't say, I want vanilla followed by chocolate. Don't you dare put chocolate in followed by vanilla, because when I get my bowl with 2 scoops, I can't tell what order they were put in. It's just 2 scoops. So in the last case, where I just want to take 2 things, I'm not putting them in order, I want 2 scoops. What are my possibilities? Well, now I can have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. Not 2, 1, I've already got 2, 1, but 2, 2, 2, 3, 2, 4, 2, 5. Not 3, 1, I've already got that. Not 3, 2, I've already got that, but I could have 3, 3, 3, 4, 3, 5. You kind of get the hang of what's going on. 4, 4, 4, 5, 5, 5. So if you think about it in terms like ice cream, I have 5 different flavors. I want 2 scoops. I can certainly have the same scoop twice. This calculation isn't either one of the first 2. There are 15 choices in this case. But it seems like there ought to be factorials and combinations involved somehow or another. Yes, there absolutely are combinations somehow or another. So let's sort of figure that out. So I'd like to know, how could I have gotten this? So what we're going to do is create a situation where I partition the numbers 1 through 5. I'm using the same example again, okay? So if I've made categories, let's say 1, 2, 3, 4, 5. All right. These are my categories. And what I want to do is say, okay, let's say hypothetically, let me erase this. Let's just pick one of our choices, or let's do a couple of the choices we just chose randomly. Let's say I wanted to pick the choices 1, 3. Maybe I want to pick the choice 4, 5. Maybe I want to pick the choice 2, 2. That's written down. How would that look in terms of the partitioning? Well, what I'm going to do is say, okay, I picked this guy and I picked this guy. Here I picked this guy and I picked this guy. Here I picked this guy twice. So what I have to do is now create a partition, okay, between the categories. Now notice if I have 5 categories, I can have at most, okay? If I have 5 categories, I can have at most 4 partitions. So in each case, it's kind of what we're doing here. So if I look at it like this, there's 4 partitions and I have to figure out where the partitions are going. And then I have 2 choices, okay? 4 partitions and 2 choices. So think about it in terms of like the bars and the X's. How many things do I have? Well, I have 6. Between the bars and X's, I have 6 places that I can put bars and X's. See, I could put 2 X's here, 2 X's here, 2 X's here, 2 X's here, 2 X's here. I can put the X's in lots of places, and I can put the bars in those places. So if I'm thinking about it in terms of bars and X's, there's 6 choices. Or I should say there's 6 things that I can do. And I had to pick which 2 places I'm actually putting the X's. So strangely enough, if I do 6 choose 2, that's my 15 that we just did a moment ago. Huh. Now, how do I get 6? Well, first of all, how many partitions are there? There's 4, not 5. There has to be 1 less. It's kind of, think of it this way. You have a big house. Let's say you have a gigantical room and you want to put a partition. 1 partition will split it into 2 rooms. 2 partitions will split it into 3 rooms, and so on and so on and so on. So the number of rooms would always be 1 more than the number of partitions, or the number of partitions always 1 less than the number of rooms. Oh, so I can think of the 6 really as being 5 minus 1 plus 2. Now, why am I doing 5 minus 1? Because there were numbers were 1 through 5. Those were the 5 numbers I was using. There's 1 less than that partition. So 5 minus 1 is 4. I was choosing 2 things. In this case here, what would serve as the N and what would serve as the R? What would be the N and what would be the R in this case here? Anybody?
N would be the 6.
I have 5 numbers and I'm choosing 2 of them.
Oh, well then 5 2. 5 is for the N.
And
R is 2. So you meant from the final combination you wrote down.
But I'm going to do this, but my N and my R are clear. I mean, I'm only picking 2 numbers, so clearly that's my R. And I only started with 5, but because I allowed for repeats, think of this partitioning case. So this is a new formula we're deriving. We've done N distinct objects choose R. That's called a permutation. And a lot of times people refer to that as an R permutation. Why? Because I'm choosing R things. If I have N objects and I'm choosing R of them, but I'm not putting them in order, I'm just grabbing them all at once, that's a combination. And again, a lot of times it's called an R combination. Oh, okay. That seems redundant, but an R combination versus an R permutation. This is a form of an R combination, but this is called an R combination with repetition. Or at least with repetition allowed. And the way that one works, it's real simple. We just figured it out. If I have N distinct objects choose R with repetition allowed, now we remove the restriction. We remove the restriction that R must be smaller than N. R doesn't have to be smaller than N. Why not? I have the numbers 1 through 5. I want you to pick 25 numbers. Wait, I only have 5 numbers. Yeah, you can just keep going. You can go 1, 1, 1, 1, 1, 25 times. Oh, I could go 1, 2, 3, 4, and then have the number 5 21 times. So how many I choose is still called the R, but because I have repetition allowed, there's no upper limit on how big R can be. N is given. I have this many things I'm choosing from. That's solid. But I can choose as many as I want if I'm allowed to do repetition. So the formula that we've just figured out, and the simplest way to write it, I'll put the R first. It's R plus N minus 1. That's the number of partitions. Choose R. Now there is no restriction on how big R can be. N is given. I have this many things, period, right? There's nothing clever in that. So in our first example where I said pick 2 numbers from the numbers 1 through 5, pick 2 numbers. So it was 2 plus 5 minus 1. That was 6. Choose 2. Okay, but let's make it a little bigger. Let's go do our ice cream shop example again. All right. Let's say an ice cream parlor. And let's say it has 20 flavors. Okay. You want 3 scoops in a bowl. Now, the reason I'm saying in a bowl as opposed to a cone, it's clever. Because see, if I do a cone, visually they're stacked, so I can see a different order. Oh, if I have scoops 1, 2, 3, visually that looks different than scoops 3, 2, 1. But if they're in a bowl, it's the same no matter how I put them. You know, I can just keep turning the bowl around. Doesn't matter what order I put them in, it would always be exactly the same bowl. So I have 20 flavors. I want to choose 3. Now, there's 2 possibilities here. Can I repeat the flavors or do they have to be different? So let's do the 2 possibilities, okay? I have 3 scoops. I have 20 choices. That doesn't mean there's only 1 scoop available. I have the big old tubs. I can get as many scoops as I want. Infinite scoops out of each tub. So, no repetition. Repetition. Repeat. Yeah, I'm spelling correctly. If I have no repetition, then the answer is simply 20. Choose 3. Okay. Chocolate, strawberry, vanilla. You know, the classic 3. You picked 3 different flavors, and the order you picked them does not matter. But couldn't I go chocolate, chocolate, chocolate? Couldn't I go vanilla, vanilla, vanilla? Couldn't I go chocolate, chocolate, vanilla? Ooh. Now, if I had to start listing all the ways that I could repeat, you all realize that would be a really, really long list. So 20 choose 3, that's 1,140 different bowls of ice cream I could have, okay? If I allow for repeats, so I could have chocolate, 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 or I could have chocolate, chocolate, strawberry. In other words, I could have all 3 of the same, or I could have 2 of the same and 1 different, or all 3 different. Then what is this one? Based on what we just did. Anybody want to help me out here? Still picking 3.
22.
So where'd you get the 22? Walk me through.
20 plus 3 minus 1.
Yeah. And that's 22 choose 3, which is not astronomical, but it is definitely bigger. Oops. Try it again. 22 choose 3. That's 1,540. I have 400 additional possibilities if I allow for repeats. 400. Now, if I asked you, can you tell me what those 400 are? Actually, you could. For example, aren't there exactly 20 different bowls that have the same flavor 3 times? Do you all agree with that? There's 20 different bowls. I have vanilla, 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 strawberry, 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 chocolate, chocolate, chocolate. There's 20 different bowls that I could have the same flavor 3 times. But then think of all the bowls where you have one flavor twice and the other flavor once. Oh, how many ways can I do that? Well, that would be 20 choose 2. Okay. And I do it twice because 2 vanillas, 1 chocolate is different than 2 chocolates and 1 vanilla. So if you actually counted that 20 choose 20 choose 2. Okay. What is that number? Well, let's see, 20 combination 2, that's 190. Twice, because again, 2 chocolates and 1 vanilla is different than 2 vanillas and 1 chocolate. So 190 plus 190 plus 20, there's my 400. I'm not asking you to list them. I'm just showing you where those additional ones come up with. This calculation's a little bit simpler. So the idea here is if I'm allowed repetition, then there's really no upper limit on how many choices I can make. And in a lot of cases, you're automatically going to repeat. So let me give you a really simple, everyday, important, classic, real life example. All right. Let's keep this really simple. All right, so let's say there are 50 employees at your work. And it's Friday morning, you're having your meeting, and it's your turn to bring the donuts. That's a pretty huge responsibility, as you know. And you don't need to get 100 donuts, but you do need to get 50 donuts, because it'd be really bad if one person didn't get a donut. I mean, I can always give up my donut, but at least allow me the opportunity to, have my donut. So I got to go get 50 donuts. Well, the donut store down the street doesn't have 50 different donuts. But then again, I could just get the same donut 50 times. I mean, we can do that way, but you all know that's not going to fly. So when you're bringing those pink boxes of donuts in, you want to see lots of variety. So let's just suppose there are 20 different donut flavors. I think that's reasonable. And the reason I think that's reasonable is my wife and I went and got donuts a couple mornings ago. It was the first time probably in a year. And I looked at the stand and there was all these donuts. It didn't matter. I still get an apple fritter every time, but it's kind of nice to have the variety. So there's 20 different donuts. Now, they've got the donut, but that donut row goes way back. In other words, there's so many of each kind, they're not going to run out of any individual kind. So that's not an issue. Imagine the donut store is really big. I mean, they have 1,000 glazed, 1,000 apple fritters, 1,000 cinnamon rolls. Sorry if I'm making you hungry, right? Maple bars. Okay, there's so many of each kind, you're not going to run out. That's not even an issue. So I'm going to go and I say, hey, I need 50 donuts. And they say, well, what kind? I don't care. Just give me a box with 50 donuts in it. I'm in a hurry. I'm running late for the meeting. So they might give me a box with 50 of the same. They might give me a box where I have some of all 20. Awesome. So the question is, how many different boxes can I leave with? Now, clearly the order doesn't matter, because when I have a box full of donuts, there's no way for me to know what order they were put in. It's just a box of donuts. They're all getting jumbled around. So the first thing we need to do in this case is identify the N and the R, because if I get them switched, I will get a wrong answer. I think that's kind of obvious. So what would the N be in this case? Anyone want to try? Am I choosing employees or am I choosing donuts?
Donuts, so it would be 20.
So the N is 20 because I have 20 different choices. And let's do it another way. If I said I'm only going to get donuts for 30 people, I'm going to get donuts for 1,000 people. It's still 20 different donuts. I still have 20 categories of donuts that I can choose from, no matter how many employees. Oh, now from the 20 donuts, I'm going to choose 50. Now, this defies the usual combination, because in the usual combination, R has to be less than or equal to N, because I can't use anything twice. But now I could have 5,000 employees. I still have 20 different donuts. So the answer to the question is 50 plus 20 minus 1, choose 50. So that would be 69, choose 50. Now that's astronomically large, but certainly easy enough to do on my calculator. So this is on the order of, if you have a calculator, this is on the order of 10 to the 16th power. Yeah, no, it's some really large number. I have a lot of choices to make. So I'm not going to think about it. I'm just going to say fill up a box. But the idea is, if repetition is allowed, it changes everything. And I'm not going to list them unless it's really small. I started with the numbers 1, 2, 3, 4, 5, and then we started listing them. That was easy because it was small. But let's just suppose I said, okay, let's go back to the numbers 1, 2, 3, 4, 5. Now I want you to choose 3 of them. Okay, no big deal. I don't want to write them all down. if I do the numbers 1, 2, 3, 4, 5, and I choose 3 of them and repetitions allowed, you say, well, is that a big deal? Well, now all of a sudden, that's 7, choose 3. That's more. It's not astronomical. Okay, I have the numbers 1, 2, 3, 4, 5. I want you to choose 7 of them. I have the numbers 1, 2, 3, 4, 5. I want you to choose 50 of them. It starts getting really big really fast, as you can see. Okay, so let's do another example. You're going to a magazine stand. All right. You're going to a magazine stand, and let's say at a certain magazine stand, there are 50 different magazines. And usually the magazine stand, each magazine will have, all of the exact same copy, and then the next position, all the same copy, and so on. And let's say there's 50 different magazines, and you're in a hurry, and you want to grab some and take them with you for reading material. Maybe, I don't know, maybe you're a dentist and you're going to put these around your dentist office, whatever. Now, when you're walking into the office, you don't care if the same magazine shows up more than once. You're just going to grab a magazine and look at it. In fact, realistically, you walk in and you're looking at everybody's reading a magazine. You go, oh, that person over there has the only magazine I'm even interested in, but maybe they have multiple copies. Okay, so there's 50 different magazines. You're just going to grab 10. And you're not paying attention to the 10 you grabbed. So you could grab the same magazine 10 times. You could grab one of 10 different. It doesn't matter. So how many choices? Oh, so that's unreadable. How many choices? So once again, I need to identify the N and the R. So in this case, what's the N? Anybody?
N is 10. Sorry, 50.
Yeah, 50 different magazines. That's the part that's set in stone. Now, I said I'm going to grab 10. I could grab 20. I could grab 1,000, but there's still 50 different magazines. So the N is 50 because that's how many things I'm choosing from. R would clearly be 10. So the answer in this case, 10 plus 50 minus 1, choose 10. And again, it's going to be a large number. So what's that going to be? 59, choose 10. A lot of choices. And always use the combination key on your calculator. So this one is on the order of 10 to the 10th. So this is in the billions. So the answer is actually that's a really big number. That's how many possibilities I have. Yikes. So hopefully you're not thinking about listing these possibilities. Okay. So in this situation here, hopefully it's pretty clear how we go about doing this, right? This really isn't very complicated. So hang on one second. I got to move a computer out of the way. I had too many cords and wires, so I had to unplug this guy. So I'm going to plug them back in now. Problem is I had so many cords and wires that were all hitting each other. There we go. I don't want to run out of juice at any point. Okay, let's do another one, a little more complicated problem. Let's suppose let's see. Let me grab my problem. Hold on a second. Where did I put it? Okay. I want to solve the following problem. Okay, if I just said solve this, how many different solutions are possible? And I don't say anything else. How many solutions are possible? Anybody just want to make a wild guess? We're going to assume the numbers are real. Okay. I'm going to make a random guess. How many answers are possible?
5 million.
5 million. Good guess. What if I said, okay, my choice, I'm going to do a half minus a half plus 100. I'm going to do 2/3 plus
Oh, infinite.
1/3 plus 99. How many? I'm going to do -6 plus 3 plus 103. How many answers do you think are possible?
Infinite.
Infinite.
Yeah. With no restrictions, there's infinitely many. I'm not going to list them because that would take me at least a half an hour to list all infinity. Okay, so let's throw some restrictions. Okay, what if I say they have to be non-negative? Still infinity. As long as x is real, it's infinite. Oh, so what if I say x has to be an integer? Oh, let me throw some restrictions on here. In fact, let's suppose, excuse me. Let's suppose I say that x has to be a positive integer. So what if I said x1, x2, x3 are all elements of z plus? Now is it infinitely many, or do you think it's finite?
Finite.
My choices for x1 now are the integers from 1 to 100. Do you agree? For x2, my choices are 1 to 100. x3, my choices are 1 to 100. Oh, that's definitely finite. Now, it's not 100 times 100 times 100 because I can't use all 100. So think of it like this. I've got 100 ping pong balls. And I have 3 slots to put the ping pong balls. So maybe I put 30 in this slot, I put 50 in this slot, and then I put 20 in this slot. That would be a solution. Okay. I can't put a negative number of ping pong balls. I can't put a fractional or a decimal number. I can only put non-negative integer ping pong balls. Okay. In this case, I can only put positive. I got to have at least one in each category. Or I can say, I can do it a lot of different ways. Now, if I said, first of all, if I said they have to be positive, then that means I must start off with at least one in each. Does that make sense? I have to start off by putting one in each because it has to be a positive solution. So of my 100 ping pong balls, after I put one in each, because the ping pong balls, I can't. Why am I using indistinguishable ping pong balls? Because if I put the number 30 here and I put the number 30 here, it's the same number. And then, that's not really the thing. I'm counting them. So if I put one ping pong ball in each of these categories, then how many ping pong balls do I truly have left to distribute?
97.
97. I'm not doing 100. I'm doing 97 ping pong balls. Oh, so that's how many I'm going to choose from. Now, I have exactly 3 categories. My N is still 3 no matter how I look at it. But now my R, since you had to have at least one in each category, my R is now 97. So the answer to the question is how many solutions, how many positive integer solutions does this have? It will be 3 plus 97 plus 1, choose 3. And that would be what? Minus 1. That would be, did I say that right? Oh, I'm sorry, sorry, choose 97. I'm looking at that. That doesn't look right. 99, choose 97. That's not that big. My calculator. 99, choose 97. That's 4,851. That's not astronomically big. And you wouldn't want to write it out, but it would look something like this. All right. 1, 1, 98. 1, 2, 97. 1, 3, 96. All the way down the line. Now, 2, 1, 97. 2, 2, 96, and all the way down the line. And then keep going until I get up to 97 here. That would be a simple way of doing this. Now, let me change the restriction. Let's just say that they're non-negative, okay? They're elements of the integers, and x1, x2, x3 are non-negative. So I can have a 0 in each category. I could go 0, 0, 100. I could go 100, 0, 0. Does that change anything? Does that change anything in my answer? Anybody? So I want to give you all the possible scenarios here, because this is a classic problem. We do this kind of stuff in linear algebra. When we do traffic flow problems and things like that, we'll say, oh, we can only have non-negative integer solutions. This is literally on day 1 in linear algebra. We're solving large systems of equations, and it might be at every intersection, here's how many cars can pass through the intersection at any, per hour or per minute or whatever. Well, the numbers have to be integers and they can't be negative. I can have no cars, but I can't have negative cars. I can't have a fractional number of cars. And there is an upper limit. So in this case here, did my N or my R change just now?
It did change, but the question how? Because
R
you
changed.
will start with 100, 0, I guess.
So 100, 0 would now be a possible answer. Agreed? So what changed? N or R? This is always the trickiest part, is identifying the N and the R. Well,
R will change. 97.
N would still equal 3.
And now R is what?
100.
Now R is 100 because I said non-negative. I can have 0. I don't have to start off by, throwing a few in each slot. So now the answer is 100 plus 3 minus 1, choose 100, which is not outrageous compared to the previous answer, but is a little bit bigger. We said the previous one, I believe, was 4851. This is 5151. We just added, and I want you guys conceptually to make sense of this. We just added 300 solutions. We added 300 solutions because before I had to have ones in each position before I started, and now I don't. Oh, so what did we add? We added the 300 solutions that have at least 1 0 in them. Okay, so that's what we did. There's 300 solutions that have at least 1 0 in them. Now, with that said, let me throw one more restriction at you. Just again, we're having some fun with this one. Again, integer solutions. But now, x1, x2, x3 are all in Z, and x1, x2, x3 are greater than or equal to 0. Well, that's the same one we just did before. And x1, x2, x3 are all even. So I can't do 1, 1, 98. I could do 0, 2, 98. So are we going to gain or lose solutions here, do you think?
Lose.
Yeah, it's kind of obvious. We're going to lose everything that had an odd integer in it, which was probably a lot. Do you think we're going to lose half, more than half, or less than half? If you just have to do a wild guess.
About half.
That, by the way, I don't know what the answer is. I haven't calculated it, but that's certainly a reasonable starting point that, you know what, I'm probably going to lose maybe half my solutions. Maybe we lose more. Now, I think it's safe to say that N is still 3, but now what's R? Remember, I said, think of it before, like there's 100 ping pong balls. It's non-negative. I can have 0. There's 100 ping pong balls, but if all my numbers have to be even, think of 100 ping pong balls, but 2 of them are always glued together. I can have 2 ping pong balls. I can have 0 ping pong balls, but I can't have 1. So what's my R now?
It would just be 50.
Maybe 51.
It would only be 50 because I can't put, an odd number. I can only put even. So another way of thinking about it, how many positive even numbers are there up to 100? Only 50. So now my R is 50. So I'm trying to give you guys every scenario so it all makes sense to you. So now my number is going to be 50 plus 3 minus 1, and choose 50. Now let's see what does that look like compared to our other answers. So that would be 52, choose 50, which is 1,326, which is actually really small. In fact, I think our last example was 51. So this is only a little more than a quarter. Oh my goodness. So we didn't lose half of our solutions. We lost almost 3/4 of our solutions. Yikes. Okay.
Is it because you have situations like if x equals 9 or x1 equals 98, you don't have like 2 even numbers to equal 100. So like that wouldn't be a possibility.
Well, no, 9820, 9802.
Oh, right.
I can still do that. But think of it because of the odd numbers, if I said, how many ways can I get, let's just say I have 6 ping pong balls left. I could go 0, 6, 2, 4, 4, 2, 6, 0. But before I could go 1, 1, I could go 006, 105, 114, 1,
Makes
2,
sense. Makes
3.
sense.
In other words, do you see? Oh, when I start filling in all those odd numbers, I actually have a lot more choices. If you're trying to justify this, by the way, which is always a good idea, always pick small numbers. When I'm saying justify it by starting to think about your outcomes, like I'm now telling you out loud, when you have thousands even, that's too many to write down. So maybe do the exact same problem, but instead of 100, maybe make it 10. So then introducing your outcomes wouldn't be quite so complicated, and then you can start seeing how things work. So this is called R combinations with repetitions. There's nothing about it that's difficult once we developed the formula. But what makes this one totally different from what we were doing before is I have n distinct objects. I'm going to choose R of them. If I'm putting them in order, that's a permutation. If I'm not putting them in order, that's a combination, but that R had to be less than or equal to n, because once I choose something, it's chosen. I think that's a word, right?
I have a question.
Yeah.
So if we choose between 0 and 100 even numbers, isn't it 51 and not 50? Because,
But putting 0 in a category isn't putting, it's not put. So think about it like the ping pong balls and the partitions. Where am I physically putting the X's?
But you can put 0 into X2.
Yeah, but you're not, if I said I have 100 ping pong balls to put in the categories, I can put all 100 in one, I can distribute the 100 out there, but I have 100 that I'm distributing. Before, when we said they had to be positive, I had to start by making sure each category already had one. So I'm only distributing 99, or we said 97 of them.
Okay, I'll think about it. Thank you.
Yeah, don't do small numbers. Okay, do the same problem, but keep the numbers really small. Would that help? And heck, make this a 4. I don't know. Keep the number small, and then all of a sudden okay. In fact, let's just do that. Let's do that right now. Let's make that a 4. And let's do, forget the even, let's just do non-negative integers, okay? So what are my possibilities if they got to add to 4? I can go 0, 0, 4. I can go 0, 1, 3. I can go 0, 2, 2. I can go 0, 3, 1. I get one more in there. I can go 0, 4, 0. Okay. Probably wrote a little too big. Okay, now, what if I start with 1? Now I can go 1, 0, 3, 1, 1, 2, 1, 2, 1, 1, 3, 0. Okay. 2, 0, 2, excuse me, 2, 1, 1. That's what I'm using 4. 2, 2, 0. 3, 0, 1, 3, 1, 0. Sorry, I can't read my own writing here. And then finally, 4, 0, 0. Sorry, I kind of did this. So 1, 2, 3, 4, 5. That's 15. How else can I get 15? My n is 3. My r is 4. You with me so far? So my answer was 4 plus 3 minus 1, choose 4, or 6, choose 4, which is in fact 15. So hopefully that answers your question, Sergey. When you're thinking about it with 100, it's too big. So I said, let's do it with 4, and we still got the same thing. If, excuse me, if I said they had to be positive integers, if they had to be positive integers, then this changed everything. Why? Because every answer that had a 0 in it would no longer be a viable solution. Oh, so if they had to be positive integers, then I believe these are the only 3 answers. If they had to be positive integers, I don't have 4 ping pong balls that I'm distributing. I really only have 1. because I'm starting with 1, 1, 1, and I'm taking that one additional ping pong ball and giving it to this guy, or this guy. Does that help?
Yeah, but what? So if you say that now the restriction is only even numbers.
Now, if I only have even numbers, what's different? Well, first of all, if I only have even, let's try to identify them. If I only have even numbers, then I have, there's one, there we go. And I believe that.
And the first one.
And there we go. So that's what, 1, 2, 3, 4, 5, 6. So if I have only even numbers, what changed? I'm no longer thinking about 4, I'm thinking about 2 sets of 2. So what changes in this formula? It becomes 2 plus 3 minus 1, choose 2, which is equivalent to 4, choose 2, which of course is 6. By the way, way easier than writing them out, but because I chose a small example, writing them out wasn't taxing, right? It wasn't overwhelming. Little detail, but not too bad. So that's where we are. I'm going to go ahead and stop here. Whoop. Oh, don't freeze on me now.